Hello, this is Aykut Attar from Hacettepe University, and this is the lecture on the scale effects problem. This is an important debate in modern growth theory, and today, in this lecture, we are quickly covering what are the main arguments put forward by different groups of growth economists. So there is this one essential reading for this lecture. It is Lang's and Pareto's scale effects in endogenous growth theory and error of aggregation, not specification. So this is a very nice paper. It has a theory part. It has an empirical part. So it will give you a nice set of information about the scale effects. So I'm going to quickly cover the main elements of this debate. So let's start. So what is the scale effect? Let's understand that. So in the first generation Schumpeterian models, there is this property that a larger workforce allocated to R&D or simply a larger population, this increases the long-run growth rate. So if L goes up, G goes up. Okay. The three most important models of this class are those of Romer, Grossman and Helpman, and Agyon and Howitt, as we know. And in a 1995 paper, Charles Jones showed that this is not true in reality. Okay, so he looked at the U.S. data, the workforce employed, basically scientists and engineers allocated to R&D, and that of course increases in the post-war era. Okay, in the U.S. But per capita GDP growth rate is largely stable in the same episode. All right, so that's the scale effect problem. So in the first generation Schumpeterian models in the literature, again in early 90s, we've seen that. So where is the scale effect in our models that we discussed in the earlier lecture? So if you look at the product variety and the Schumpeterian model that we discussed in earlier lectures, in both models, the partial derivative of G, the long-run growth rate, with respect to L, basically population or the labor employed in the final goods sector, this derivative is positive, meaning that there is a scale effect in the model. So obvious question is, of course, how to sterilize the scale effects, because growth theory is more or less a realist scientific project, and growth theorists always looked at the data at all times, and of course they want to understand what is the real reason that makes these models prone to this problem. Okay, so the question is how to sterilize such scale effects in the Schumpeterian growth models. Now, there was this one solution, and it is called semi-endogenous growth. So in the mid-90s, there were three important papers, one actually published by Charles Jones himself in 1995, and then there's Samuel Kortum's 1997 models and Segerstrom's 1998 models. So these papers basically assume that there are actually decreasing returns to knowledge in the production of new knowledge. All right. So remember that each and every endogenous growth theory basically assumes, sometimes this is a complex one, sometimes it's a simplified one, but basically they assume that there is a knowledge production function or there is a technology production function. So if you put some inputs into technology, there is this R&D inputs, R&D expenditure, whatever they are, and then you create new knowledge out of this, right? So if we look at Lang's and Pareto's papers, so they start with the simple characterization of knowledge production. So here AT is some aggregate productivity measure, and this aggregate productivity measure basically grows as a result of R&D investments. Now R&D investment here is modeled through LAT. So LAT is the labor employed to the production of A. Okay, and delta is some positive constant that basically determines the productivity of R&D. And AT to the phi, so this term indicates that existing knowledge is important for creating new knowledge, right? And if you look at the real world, this is really true. Why? Because imagine that we are writing a new paper. We always look at the literature and we learn from the literature, certain models, theories, data, etc. And then we build new knowledge by using this existing set of knowledge. Now, decreasing returns is captured by this assumption. So this parameter phi is between 0 and 1. So there is decreasing returns with respect to knowledge. Okay? There could be an extended definition, extended specification of this that puts an exponent here, such as lambda. So that could be also an interesting addition. But for now, the main discussion revolves, so the scale effects discussion is revolving around this parameter phi. Okay? So of course, the models presented in these papers are much more complicated than this, but essentially they all have this type of property, phi less than 1. All right. Now, if you write the growth rate, a dot divided by at, this one, a dot t divided by at. Now, this growth rate must be equal to this one for all t, right? Now, we imagine that population is growing because we are looking at this long run, post World War II era, and we see that population growing in these economies. And back in 1990s, economic growth theorists would still take exogenous population into account in their models. And then, a common assumption in such models, so of course this is a result in a general equilibrium setup, but basically the share of R&D workers is going to a constant, all right? So of course that depends on many things, technologies, preferences, etc., policies. But in a population is growing, then a growing portion of this is allocated to R&D. Okay. Now, if you look at this equation, if we want a constant productive growth rate in the long run, then the numerator and denominator should grow at the same rate, right? And if that goes to a constant, LAT grows at the rate of population growth, all right? Then balanced growth assumption implies that growth rate must be equal to n divided by 1 minus phi. Now, you must compare this growth rate with the earlier growth rates that we found in the Romer or the Agyon-Howitt models, all right? In those models, growth rate was depending on preference and technology parameters. Now, most of that is gone. Why? Because now GDP per capita growth rate must be associated with population growth rate, okay, because of these assumptions. So in that sense, and since we take n as exogenous, the entire growth rate, although it is scale independent, it becomes semi-endogenous. Most specifically, the share of R&D allocated to research, this constant there, does not appear in the growth rate. All right. So that implies, yes, semi-endogenous growth models correct for the scale effect problem. They sterilize scale effects, but in the meantime, the policy relevance is gone. Okay. Right here. So growth does no longer depend on preference and technology parameters. That would change the R&D effort. So from a policy perspective, we don't like semi-endogenous models, all right? Because usually population growth rate is not something that, policies could easily change. That depends on, sociological characteristics, of course, the level of economic development that an economy is in as well. But policy is almost always not effective in, changing population growth rates. And so the growth rate does not depend on R&D subsidies or research policy more generally. All right, so that's the problem. That's the main problem in semi-endogenous models. And of course, there's a second solution, right? Because we don't like it. We don't like the result there. So what are these? These are called second-generation Schumpeterian models, and 4 of them are important. So they are developed in late 90s. I think the earliest innovation is due to Pareto, because Pareto, although he published the paper at 1998, he started working on this on 1994, I guess, or 1993 as a PhD student. But anyway, so these models introduce not only vertical innovations but also horizontal innovations. All right, so they created this two-dimensional landscape of technological progress, and they modeled knowledge production at the firm level or the sector level. Okay, and it's basically this property that solves the scale effects problem. In this respect, I must emphasize that. So once they introduce horizontal innovations within a model of vertical innovations, then they no longer need to assume decreasing returns to scale. So that's the important part. So that's the main assumption that separates these two groups of growth economists. All right. So first and second generation Schumpeterian models, they do not assume that there is decreasing returns to knowledge, because that's a shaky assumption. I mean, it's not certain that there are actually decreasing returns to knowledge in the actual economy. So for that reason, they look at the knowledge production at the firm level, and that solves the problem. Why? Because now an increasing workforce of R&D is allocated to many sectors, many firms. All right, and so for this reason, they argue that once we correctly measure R&D workforce diffused over an increased number of innovating firms, the scale effects disappear. So the problem is not about the specification of the knowledge production function, but the problem is about how do we measure knowledge production. All right. So here is a toy model. Here's a toy second generation model. It looks a little bit complex, but it's not actually. So let me explain. So here in this model, I indexes the firms or the sectors in the horizontal dimension of innovation. All right. So they lie in an interval from 0 to FT. So FT is the number of firms or number of industries that actually innovate. All right. And in each industry or the firm, there's this production function. So YTI is the production of good I at time T, and that depends on two things: productivity of firm I at T, and how much labor is employed to produce that good in that particular firm or sector. Okay, that's it. And all these together create this composite good or composite final good that you may call GDP. All right. So basically, different sectors or firms, these outputs are collected together in this constant LCO substitution, production function, so that there's this final good. Now, if you look at knowledge production at the firm level, as you see, this is the same function that you see here, but instead it is assumed that phi is equal to 1, so there is constant returns to scale with respect to knowledge, and it is written at the firm level, right? So for each firm, there is this knowledge production function, but then this aggregate term here is the average productivity. So what happens here is that once a firm tries to create new knowledge, they benefit from the existing knowledge in the economy. All right. Why is that important? So this is like a spillover effect. Of course, it simplifies the analysis a lot, but it is also somewhat realistic, right? Because if a firm tries to invent new things, the knowledge accumulation created for other sectors in other firms, they might be relevant, because usually here we are talking about science and technology, so they all are connected. Okay, and there is this aggregate resource constraint as well. Okay, so what does it tell you? It tells you that the total population or the workforce is allocated to good production and knowledge production, and for each firm, the total must be equal to the total. If this is total demand, this must be equal to total supply. All right, and again, we still assume that population grows or the workforce grows at this constant rate n. Okay, here. Of course, we might be asking how the number of firms change. I will be talking about this in a moment. So for now, we can just assume that it will grow according to some horizontal innovation specification. Okay. So now, to simplify the matters a lot and just to convey the main message about how second generation Schumpeterian models actually resolve the scale effects, actually sterilize the scale effects, we just imagine a symmetric equilibrium. All right. So in the symmetric equilibrium, each firm's productivity is equal to the average productivity, of course, and labor's, types of labor allocated to goods production and knowledge production are equal. All right, equal across firms. Now, if this is true, if you connect these with the earlier equations that you see here, then we got this. So we got this aggregate GDP being equal to the number of, it's a function of number of firms, it's a function of average productivity, and it's a function of how much labor is allocated to good production. Okay. Now we also simplify by assuming that, so here we are bypassing the entire general equilibrium framework just to, again, understand how they solve the scale effect. So we assume that the a fraction S of labor force is allocated to research. All right. So S is, of course, endogenous. If we write the entire general equilibrium version of this model, and we will do so in later weeks, so we're going to look at some of the second generation Schumpeterian models. But for now, we take S as given, but again, be careful, S will be an endogenous variable once we introduce general equilibrium dynamics into this framework. But for now, we are assuming that S is given. So if a fraction S of the entire labor force is allocated to research, so this is the entire demand for research, right? So this is firm level average times the number of firms is equal to the total supply. And then, of course, the remaining fraction is allocated to goods production. Okay. Then we can define GDP per capita. All right. So what am I looking at? I'm looking at this. So this is aggregate GDP, right? So I divide both sides of this equation with LT, right? So YT divided by uppercase Y divided by L. And I got this. How? Look at this. So if LYT is divided by LT, then I have 1 minus S divided by FT here, right? So 1 minus S divided by FT, so that FT goes up there. So it is FT, theta minus 1, AT, 1 minus S. All right. Now, quickly, of course, we can write the growth rate, right? Assuming that S is constant. And since S is bounded, so, S is a bounded variable, so it will not go to positive infinity or negative infinity. So it will not grow in the long run, which makes a lot of sense. We can basically write the growth rate in the long run as the, growth associating with the horizontal innovation and growth associated with the vertical innovation. All right. So existing firms create new knowledge, so they go on the vertical direction here, and then there is new firm entry on the horizontal dimension, so there's this firm growth rate as well. All right. So again, GDP per capita growth rate is then equal to theta minus 1 G of FT plus G of AT. All right. Now remember product innovation channel, so we must have some theory about GFT. And in the second generation Schumpeterian models, we have nice theories about how firms enter, why firms enter, and how firms enter. There's this return rate of firm entry, so that depends also on entrepreneurship behavior, cost of establishing businesses, etc. But for now, again, since our purpose is only to display that how second generation Schumpeterian models actually resolve scale effects debate, we just assume that total number of firms in the economy is just proportional to the number of people. All right. This is not just a simplifying assumption. In most of these models, G of FT would actually be equal to, in the long run, to the population growth rate. All right. So it is not really a big deal to assume that FT over LT is just a constant. All right. Now, if that's true, again, G of ft must be equal to n, so this part becomes the semi-endogenous part, semi-exogenous part of this equation. But again, since now we are understanding that growth at the firm level is occurring at this rate, okay? So S is the share of workforce allocated to R&D. Delta is some productivity parameter for R&D, and 1 divided by eta basically represents that fraction. All right. Now, once again, policy relevance is appearing here because there could be some policies, some R&D subsidies, some other type of research policies that might affect S. All right, in a typical private ownership economy. So then that's how we solve it, right? As you see, S will be endogenous determinant equilibrium. And as I said before, we can actually write more complicated stories of how FT grows. Okay, and that also have, of course, policy implications. Okay, so I will have a few final remarks. One thing is that I think the debate over scale effects is largely over, right? So the main reason I think is that they make sense empirically. So if you look at Lenks and Pareto's paper, it is really hard to sustain the proposition that growth rates in the long run are proportional to the population growth rate. So that's actually the reality is exactly the opposite, especially for the modern times. There are some papers that kind of show that there is a scale effect in the very, very long run. So if you look at like hundreds of thousands of years, humanity created increasing growth rates in the very, very long run, along with increasing population growth rates. But for the modern times, it doesn't work. So that's just one reason. Another reason is that it is just working in theory, right? So it works well. And also there are other papers, most notably by Jacob Madsen. So those papers look at the aggregate macro data, sometimes industry data, and they find support for second generation Schumpeterian models. Okay. I also recommend one additional reading. So this is by Bloom, Jones, Van Reenen, and Webb. So they ask a really nice question: are ideas getting harder to find? Okay. So it is slightly related with the scale effects discussion. So they go at the industrial level and they try to understand, although R&D effort is growing, maybe R&D productivity is decreasing. So you may imagine that R&D productivity term here is basically delta times AT. So if you look at this model, R&D productivity is not changing, right? But in the data, they find some support for that hypothesis. All right, so that's an interesting reading. And the last remark is that in the last couple of weeks of this semester, we'll be focusing on some of the second generation Schumpeterian models. All right, mostly we're going to look at Pietro Pareto's models. Why? Because I think they are nicer than other types of second generation models. Pareto works with this hypergeneral equilibrium setup. So there's households, there's firms, there's this, the models are consistent with micro evidence in terms of industrial organization and also macro evidence in terms of, gross ratios such as consumption to GDP ratio, investment to GDP ratio, R&D expenditure to GDP ratio as well. All right, so for these reasons, I like these models, and also some versions of the second generation Schumpeterian models developed by Pareto are also actually relevant for understanding industrial evolution as well. So since I have this obvious bias for very long run growth issues and development issues, those models are they seem nicer to me compared to other models in the literature. Okay, I think that's for all. Thanks for watching and stay tuned for other lectures. Thank you.